Hi, so in this video, I want to talk about some application of parametric curves that we've been learning about. Um, the topic I had in mind is what's common in between driving sunglasses, LCD screens, and modern 3D movies that you might see. Um, so let's get right to it. I think you'll find this pretty cool. Okay, so some of you might know this, some of you might not. For all three of these things to work, it utilizes what's called polarization of light. So uh, let's talk about it. Okay, so the beginning is a little bit weird. Uh, the parametric curve of photon, let's say, photon is a particle of light, might look something like this, and I I apologize, this looks a little bit weird. So I just want to describe parts of it. This this letter that looks like a W is Greek omega. This is the frequency of light. So higher it is, the higher energy light it is. Um, and then this I, some of you might have seen it, some of you might not. This is the complex imaginary number. So it's something like square root of -1. And you might be wondering, how do you take e to the power of imaginary number? So if you have taken maybe differential equations course, this might be something that's covered, but it's okay. This little bit is not really necessary to get the gist of what we want to talk about. So I'm going to simplify the situation. Just ignore the notes about this part. What's important is that for these, let's say, photon that's traveling, I'm going to always assume that it's traveling in positive z direction. And instead of writing these complicated, complex expression, you could just think of it like a wave. So sine or cosine waves, so some kind of sinusoidal waves. So maybe you could rewrite it like this. So use cosine or sine function. Okay, and these numbers A and B could be complex numbers as well, but it doesn't really help the situation. So you could just imagine them to be real numbers. Basically, just ignore everything I've said so far. I just have to say it. So, I'm not lying to you, but really, this is not the important part. Okay, so let's first talk about what linear polarizer is. So linear polarizer is like a film. It's like a semi-transparent film, and it has a direction. So let's say you're holding a polarizer. So it's like a piece of plastic, and let's say it's polarized in this direction. And what it does is that polarization of light has a direction, and it blocks all the light that's not going in that direction. So if, let's say we have a photon wave that's maybe perpendicular to the direction of polarization, as it tries to pass through the polarizer, it will just be absorbed by the film. I mean, it'll just get blocked. But if a light comes along having the same direction of polarization, so it's from this point of view, horizontal polarization, then it allows it to pass through. So that's what happens if it's orthogonal or parallel to the direction of polarization. What happens in between? So let's say the directional polarization is horizontal like this, and light that's polarized some kind of diagonal angle tries to pass through. So then what happens? Uh, if you have angled polarization like this, what happens is that it might pass through or it might not. So there's some probability associated with this. So what is the probability? Well, the probability that it passes through is going to be, you can make a right triangle like this angle, um, is proportional to the square of the um, uh, sorry, component projection. There, I said it. Okay, projection. And there's some probability that it gets blocked, right? So probability that it passes through is cosine squared of the angle. And probability that it gets blocked is 1 minus cosine squared. But using a trig identity, that's the same thing as sine squared. Okay. So if it passes through, then the photon that passes through is now going to have the same polarization direction as the film, right? If it gets blocked, then it's gone, right? So the only light that passes through is going to have the exact same polarization direction as that's prescribed in that polarization linear polarizer. Okay. Um, of course, when we're looking at light, uh, we're not just looking at a single photon. So it's film is bombarded with lots of photons. So some of them get through, some of them doesn't get through. The intensity of the light is lowered if it's not perfectly polarized along with the polarizer. And I think there's a, let's see. There is a, oh yeah, so there's a physics law that describes this. So if I naught is the initial intensity of the light, and you're making angle theta with the polarized light versus the linear polarizer film, then the intensity of the light you see is going to be reduced by a factor of cosine squared. Okay, so how is this related to the other things that we were talking about? Well, driving glasses work this way. So if you have a driving glasses, it is usually polarized in horizontal direction. Why is that? Well, when you're driving along the road, excuse my drawing here, let's say there's a bright light outside, maybe you're kind of driving into the sun. What happens is that, so the light that comes from the sun is polarized in all different kinds of ways. So there's no preference in which direction it's polarized. But if it reflects off the road, it tends to be, the polarization tends to be vertically aligned, perpendicular to the road. So what the sunglasses does is that it tends to block the light that's coming off the road. Not perfectly, but more light that reflects off the road is reduced by your sunglasses. So the effect is that you have less glare off the road while you're driving into the sun. Um, so that's how driving glasses work. And of course, like, it kind of tints everything because some of these light that's polarized in different direction gets blocked. So you get less intensity in general, but it blocks more of the light that glares off the road. So that would be a useful thing when you're driving towards a bright road. Okay. Okay, so that's the driving glasses part. So let's now talk about LCD screens. So LCD stands for liquid crystal display, and usually it comes in 3 different layers. Um, so behind the screen, there's some light source. So let's say the light is emit. Let's imagine we're looking at the laptop screen. So behind the screen, there's light that's shining through, and it passes through one layer of linear polarizer. So there's different ways this could be oriented depending on which electronic device you're looking at. But I think the most common way for this to be polarized is diagonal direction on your LCD, maybe computer monitor or laptop screen. So it's usually diagonal. So the light that passes through the first layer is going to be diagonally oriented. And the middle layer, that's the liquid crystal display. What it does is that if that portion of the screen is kind of stimulated with like electricity, some kind of voltage, then what it does is it twists uh, the, the polarization orientation through the liquid crystal display. And it might be twisted in maybe opposite diagonal direction. And the amount of twist could be controlled by how much voltage we're applying on the LCD screen at that pixel. And there's another layer of polarizer in the front of the screen. So if the light gets twisted in such a way that it's perpendicular to the linear polarizer in the front, then it gets blocked and it appears black or dark, right? So that light doesn't make it through the screen, and you might not see it. Okay? But if it doesn't get twisted and it's going the same direction, then it passes right through, and then you'll be able to see it just fine. So the light that's coming from the back of the screen reaches your eyeball. Okay, and you can kind of control like how much of the light goes through by twisting just some of it, so the intensity could be controlled by cosine squared theta. So you can kind of get the correct intensity that you want for that pixel. And I'm saying pixel, but really you're doing it for 3 different color light, right? So you're doing, there's some pixels are red, some are green, and some are blue. And each of those intensities controlled individually. And if they're all coming through, it looks white to you. If they're all being blocked, then they appears black to you. And that's filled up with the screen, and that's how you get the screen. All right. So I just kind of want to kind of show it to you. Let's see if I could do this. Okay. So I have a laptop in front of me, and okay, this is really difficult. And I have a pair of driving glasses. Okay, so if I twist this, you might see that in this diagonal orientation, it looks dark, screen looks dark through the lens. But if I twist it in other ways, it looks brighter. And it kind of gets dark when I hold it in this angle right here. And if I twist it all the way through, it gets light again. Okay, so this laptop that I have with me right here is kind of polarized in a diagonal direction. My tablet right here is polarized in a vertical direction, but I can't show it to you because I'm recording using it. Maybe I should have brought a mirror, but You get my gist. Okay. I just kind of want to tell you a story about my friend who knew how this LCD worked. And what he did was he got a laptop, and he removed the third layer. Right? So he removed the third layer, the linear polarizer. So all the lights are still kind of getting through. Some are twisted, some are not. But all the light is going through. So it looks, the laptop looks white at all times. But what he did was he also special ordered sunglasses that were polarized in diagonal uh, direction that matched his laptop screen. And the glasses themselves were $20, but because he special ordered it to be polarized in a weird direction, he had to buy like 20 pairs of them for them for them to make it worthwhile to make like produce these sunglasses. So he spent quite a bit of money. But what he got was a laptop that has a white screen that you could only see the screen if you put on this special sunglasses that he bought. So I thought that was kind of cool. I saw it worked as intended. Although if you kind of look at the laptop from extreme angle, you can kind of see a little bit of what's going on. It's not perfect, but I thought that was amazing when he showed me how this thing worked. Um, yes, so I don't know how practical this thing is. Like it can be used as a privacy device, right? You could be doing something on the laptop during the bus, and maybe somebody's not looking over your shoulder. So that's kind of cool. Although they might think you might be a weirdo or something. All right. So that's the laptop mod that my friend Nathan made. Okay. Let's talk about 3D movies. So there are a lot of 3D display technologies. So probably the oldest one that I can think of is one of those red-blue glasses, where so how they work is pretty clear. Okay, the movie is displayed in two colors, red and blue. Sorry. I'm just gonna color it blue and yellow because those are the color that I have readily available. And what it does is that if you see a blue image through a blue film, you don't really see much of it. But if there's a yellow image, you can kind of see it through the blue film and vice versa. So you're getting two different images from left and right glasses, and you can kind of see the 3D effect that way. So the way we perceive depth is by comparing the two images that we're getting from left and the right eye, and then kind of deducing how far away they must be for it to be off by a certain amount. Okay, so that's old technology. This gives you a headache because the color just isn't right. Okay. A similar idea, I've never used this version of a 3D technology, but you could have left and right shutter glasses. So uh, what could happen is that you could have a screen that flips back and forth between your left and right images. And you have a special sunglasses that has a shutter that kind of goes back and forth, and the left and the right eye kind of opens up, taking turns, synchronized in such a way that you see the left image through your left eye and the right image through your right eye, and it's going so fast that you can't it looks like you could see the image. So I don't know how well this works, but you could have a technology that way that works that way. Um, this one of my favorite technology is Nintendo 3DS. So this is a personal device, personal gaming device that has a small screen that's sitting in front of you. And this 3D technology doesn't require you to have a special glasses. This is especially nice for me because I already wear a set of glasses, right? It's always annoying to wear um, some special glasses on top of my glasses. So how this works is that the screen has lots of vertical slits, and you're looking at it with two eyeballs. I know your eyeballs isn't oriented that way, but it's hard for me to draw. Um, and you're looking at the screen through these slits. But because two of your eyeballs is looking at the screen in different angle, you see different images behind the slits. So that's how 3DS is creating an image that looks different from the left and right eye. The drawback of this is that you have to be holding it at the right distance. So you can adjust how far you're holding it, and it also depends on how far apart your eyeballs are. And it doesn't. It only works for one person, right? So if somebody's off to the side looking at your screen, uh, you're not going to get the same 3D effect. So that's kind of nice, but again, this kind of gives you a headache after a little while. So I think about 15 minutes I can play comfortably, and no more than 30 minutes I can play with this 3D feature on. So that's Nintendo 3DS. And let's talk about modern 3D movies. So there's a way to get two images to your eyeballs um, using polarization of the light. And you might be thinking, oh, I know how they do this. Maybe they just have sunglasses that's polarized in horizontal and vertical orientation in such a way that you see one image with the vertical polarization and you see another image with horizontal polarization. This is not quite how it works. The problem with that is that a lot of people do not look at the movie head on. A lot of people like to kind of get comfortable and look at the screen maybe diagonally. And if we polarize the light that way, tilting your head could blur the image, and then you're not getting the 3D effect and you're getting headaches, right? So this is not quite how it works. What it does is it gives a different type of polarization called circular polarization. And I want to describe to you how this works. Okay, so how does this work? So there's a light source and some unpolarized light is coming through. And then there's a film of linear polarizer. So light coming through it has a particular orientation. And let's say that it's polarized in such a way that it's kind of, let me draw it, let's say X and Y axis. It's polarized in such a way that it's 45 degrees this way. So it's along the line X is equal to Y. So this is what it might look like. Don't worry about the 1 over square root of 2 in front. That's needs to be there for technical reason. But basically, X and Y are both the same cosine wave. They're equal to each other. So the light would go back and forth kind of going wave in this way. All right. So what does this quarter wave plate do? What it does is that it takes one of the directions. So let's say in this example, uh, it affects the y component of this parametric curve. And what it does is that it takes this cosine curve and kind of delays it by quarter of the period. So cosine repeats itself after 2 pi. So if you delay it by a quarter, I'll be delaying it by pi over 2. Okay, but there's a trig identity that says that if you take a cosine wave and then shift it by quarter of the period, then the resulting function you get is the sine function. It's the exact same shape wave pushed to the right by just a quarter of the period. So this thing is actually the same thing as sine. But now what we get is what's called circular polarization. So we have cosine and sine in xy plane. Okay. And let me draw what it does. We know what cosine and sine does, right? It draws a unit circle around the origin in counterclockwise direction. So it's traveling in z direction, but it's drawing a counterclockwise circle throughout the z-axis, and it's traveling that way. So you can actually polarize it, not just the direction. You could polarize it in such a way that it spins, and this is what that does. Okay, so what? You have a circular polarized light. How do you distinguish image that way? So what your 3D glasses at modern movies. So if you've seen movies, 3D movies recently, you have these real 3D glasses, and what they do is pretty much do the exact same thing at the. You just hit the quarter wave plate first, and then you look at the linear polarizer afterwards. So what happens? So let's say you have something that's counterclockwise polarized. So it's a cosine and sine. And you hit it with the exact same quarter wave plate. So sine is now delayed by another quarter period. And if you take the sine wave, shift it to the right by another pi over 2, then what you'll get is negative cosine. So light that was polarized, x equals to y, turns into circular polarization. And then after going through quarter wave plate again, it's polarized in the other diagonal direction. X is equal to negative y because cosine and negative cosine here. Okay, so and then you could orient this final linear polarizer in such a way that you might block it if you don't want a counterclockwise polarized light. If you twist it, then what you get is you could receive clockwise polarized light. So what's happening in the movie is that they're playing two different images with clockwise and counterclockwise polarization. And on your glasses, there's this quarter wave plate and linear polarizer. So only the right direction turn could go through that lens. So you're getting one image at a time. And The advantage that I mentioned with this circular polarization is that it doesn't matter how you tilt your head, right? Like you can look at it uh, leaning on your hand, and if it's going clockwise, it's still going clockwise, even if you tilt your head. So um, the tilt of the head doesn't destroy the 3D-ness of the movie, which is pretty cool. It's a interesting innovation. Um, I don't have the real 3D glasses with me, but next time you go and see a 3D movie, when it's safe to do so, I recommend you steal the 3D glasses and do this experiment. So you could do this with your friend who you went to a movie with, and look look at each other's glasses, one eye at a time. So you can kind of close your right eye and look through your left eye, or close your left eye and look through your right eye. And the light that kind of passes through your um, lens is circular polarized. So when it gets to the other person, you're only gonna get one of the images. So when you look through the glasses with only one eye, you could see one of their eyes, and the other one looks completely black. So depending on which eye you open, you only see one of their eyes at a time, which is pretty cool. Um, you could, if you don't want to nerd out in the theater, you could go to the bathroom and do this with a mirror as well. You could do it by yourself if you wanted. Okay. Anyways, did you find that interesting? Anyways, this is where I'm gonna end the video now. I'll see you later.